Hello students of statics, here is an example based upon two-dimensional vector resultants. Okay, so what we have here is that we are given in the problem statement the resultant force of the tension in these two ropes has to be directed vertically upward. Let's go ahead and draw that resultant force. It's going to look like this. So FR has to be vertically upward, so we know what direction it's going in. One of these ropes, we're going to call that F1, has a 200-pound tension and is pulling 30 degrees from horizontal. The other one has an unknown magnitude force and is pulling 45 degrees from vertical. And we want to find the magnitude here of F2 and also the magnitude of F sub R. Okay, so there's actually two different ways that we can solve this problem. So let's take a look at those two different methods. We're going to have method 1, which is a graphical solution. All right, so in doing a graphical solution, we are going to base this upon our resultant equation, which is that F1 as a vector plus F2 as a vector is equal to FR. Right, resultants are simply the sum of things. In this case, it's going to be the sum of these two vectors. Now, this equation is only true in the vector form because these force vectors are not all going in the same direction, right? In a one-dimensional problem, you could say the same equation was true for a scalar and not include these vector lines above, but in this one, we need those vector lines. So what we can do here is we can actually create a triangle based upon these three vectors. So let's start with our F1, 30 degrees above horizontal. So that took care of this one. Now we need to add to it. We're going to go tip to tail. We're going to add to it F2, noting that FR needs to be vertical. Okay, so FR needs to be existing along this line here. So as we add F2, it's going to come here at 45 degrees from vertical, which is also 45 degrees from horizontal, and that gets us to the same place. Essentially, we did tail to tip, adding together this side over here, gets us to the same place as our resultant force, which is going to go from here up to here. Right, so on either side of this equation, we basically began and ended at the same place. Now we can go through and define some of these angles. We said that this angle here was 30, therefore this angle here will be 30. This angle here is 45 because this angle here was 45. We also then know that this angle here is 60, and by doing some math, essentially taking the sum of the internal angles being 180 degrees. The angle that's left for this upper angle here is 45. We also know that F1 has a magnitude of 200, and we want to find the magnitude of the other two. All right, so in order to do that, my favorite rule for finding these sides and angles of non-right triangles is the law of sines. The reason I like the law of sines is because it's just simpler than the law of cosines. And so now we have the magnitude of F2, which is unknown, divided by the angle opposite it, okay? So the sine of 60 degrees, and this is going to be equal to, now I'm going to use the magnitude here of F1, so that's 200 divided by the opposite angle there is the sine of 45 degrees. And I could do the same thing to solve for FR, and so we could write here that FR divided by the angle opposite of it, which is 75, sine of 75 is equal to, I'm going to use the same fraction here, 200 over the sine of 45. So out of the top equation, we can find that F2 is equal to a magnitude of 244.9. That's also in pounds. Of course, these are pound force because all pounds are in pound force in statics. And then we have the resultant force, FR, equal to 273 pounds. Okay, so that's our graphical solution. Creating a triangle which essentially interprets this equation into a figure. Okay. The other way we're going to solve this problem is we're going to use this same basic equation, f1 plus f2 is equal to fr, all those being vectors, and change them into vector components. Okay, so let's leave that equation visible here for just a second. Come down here and say we have our method 2. We're going to use vector algebra. All right, so to use vector algebra, I need to write the vector components of each force. And so I have that F1 as a vector has a known magnitude. That known magnitude is 200. I'm going to use the bracket notation here. So 200 magnitude, and then it's going to be the cosine of the 30 degrees, because cosine is the adjacent angle, gives me that horizontal component. And then I'll have 200 and sine of 30 degrees. Now both of these will be positive values because both the horizontal and vertical components here of F1 are positive. Now I do need to go ahead and define, I'll go ahead and draw it up here. Actually, I'll draw it on my main coordinate system, that I'm assuming here that this is x, and I already drew my y, so a horizontal to the right x and a vertical y. And then I now can write the components of f2 as a vector. So f2 has components in unknown magnitude. So this is going to be f2, and it's going to be the sine and cosine of 45. So it doesn't really matter actually with 45 whether you pick the sine or the cosine. Because it is a vertical angle, we'll go with the adjacent side to the from vertical angle sine of 45. Now this, because it's going to the left, needs to be a negative component by observation. And then we have f2 cosine of 45 for its vertical component, and that one will be positive. And then the last term we'd have is that FR is going to be equal to 0 because it has no x component, comma, FR. 100% of the magnitude of FR is vertical. Okay, so now we can bring these together inside our equation. F1 vector plus F2 vector is equal to FR vector. We can split out x and y versions. The x version of this equation would tell us that 200 cosine of 30 minus F2 sine of 45 is equal to 0. And then the y version tells us that 200 sine of 30 minus, I take that back, plus the component here of the F2 in the y direction is positive. So F2 cosine of 45 is equal to 200, equal to FR. All right, so now I have two equations with two unknowns, those unknowns being F2 and FR. If you solve the x version of that equation, because there's one unknown up there, we end up with F2 equal to 244.9 pounds, and FR through substitution equal to 273 pounds. Shouldn't be a huge surprise that we got exactly the same values, just in two different ways, okay? A graphical approach on top and a vector algebra approach on the bottom. And each one is completely valid. Now, if you're adding together more than two vectors, the graphical solution is going to get a little more complicated because you'll essentially have some kind of a four-sided figure that you need to figure out the angles and components and things of. You couldn't use law of sines, you couldn't use law of cosines. So really, if you get 3 plus vectors, or greater than equal to 3, maybe I should write that way instead. Greater than equal to 3 vectors, I'm probably going to use vector algebra, but certainly for two vectors, adding them together, the graphical solution works just fine. I hope that sheds some light on these different approaches. You're totally welcome in my classes to take either approach in your problem solving.